We're going to continue on with Lesson 6 from Ka Chemistry, calculating pHs from Ka values for weak acids. We're on number 63 of our homework assignment. Let me read it with you. It says saccharin, it's just a sugar substitute, is a weak acid. Gives us a pKa of 2.32 at 25 degrees Celsius. It ionizes in aqueous solution, and we can see the ionization. The molecular form of our weak acid in dynamic equilibrium with the proton and its conjugate base. What is the pH of a 0.1 molar solution of our substance? Well, if I think about this value, pKa, that might be a unique look to something that we haven't yet seen. Of course, we know pH, we know pOH, and those are all found by negative log of the hydrogen ion concentration. When we're given pKa, that's really just the same value that has been negative log to turn it from Ka into a pKa. So of course I understand that the Ka expression, no numbers, but the Ka expression is found by taking the products over reactants, the ions over the molecule, the dissociated form over the undissociated form. If I keep repeating myself, we might soon learn that it is indeed this expression. Conjugate acid, conjugate base, set over the molecular form of the acid. So here we have HNC7H4SO3. Alrighty, so here's our expression. How do we turn a pKa into a Ka value so we can ultimately solve for the pH? Well, just as if we had pH, and we wanted to turn that into hydrogen ion concentration. I'm just reminding us of a formula we have been practicing quite a bit here lately. pH is negative log of hydrogen ion. Remember how we manipulated that to say if I wanted the hydrogen ion, it was the anti-log. So the 10 raised to the, and that could be the caret key, to the negative pH power. Well, that's all we're going to do here. We're going to take the pKa and raise it 10 to the negative. Oops, I'm sorry, I just did that backwards. I can get Ka value, you have to erase with me, I'm sorry. Ka can be pulled out of taking 10 raised to the negative pKa. So what we want to do first is to get this Ka value, and then we can set up an ice chart and start some work here to find that pH. So 10 raised to the negative 2.32. 10 raised to the negative pKa. So let's hit that on our calculator. We have to hit 10 raised to the negative, see how I'm making that a negative sign, 2.32. And we get a number. That number now represents the Ka value that we are going to place into our problem, 0.004786. There's the Ka value we can now plug into our expression. I'm going to come down and give myself some work room here and just kind of set up an extended page where we can set up our equilibrium. So number 63 continued here. We have our molecular form of the acid, and I'll just rewrite the equation, HNC7H4SO3 in dynamic equilibrium with its conjugate acid and its conjugate base. We have an initial, a change, and an at equilibrium concentration. And this one has been already eliminated the water for us, making the ice chart like this. We were given initial concentration of our molecular form of the acid as 0.1, and we know yet no ions have been made. Now remember, when we want to know pH, ultimately this is the box we need, isn't it? Negative log of the hydrogen ion concentration is indeed calculated to find pH. So this is what we're going to solve for. We know that ions get made. Let's call those values X. So at equilibrium we have X ions of hydrogen and we have X ions of its conjugate base. We also know that the molecule gets consumed, and so technically we know this is 0.1 minus X, but we have indeed been practicing what's called the 5% rule. Let's assume 5%, and then we can just double check. It just simply makes the math a little bit easier. So instead of putting in 0.1 minus x, let's leave it at 0.1 molar, checking the percent ionization of x over 0.1 to make sure we are indeed below 5%. Vast majority of the time we do obey the 5% rule. So do you remember how we calculated by going 10 raised to the negative pKa, 2.32. And when we found that value, we wrote it down up above, 0.0047863. Plenty of decimals there. There's my Ka. Knowing that the value of x times x can be written as x squared over 0.1. 0.1 times 0.0047863, square root that answer, and we get a value of x. Now let's hit that together. Be sure you're hitting it correctly with me. We had this value, 0.004786. We want to simply go times the concentration of 0.1, and we square root that answer, and we find our value of x. Is your calculator matching mine? 0.02. Let's carry some decimals. 0.0218776, just to write out the whole screen there. Remember, that was the value of x. Before we proceed, let's check the 5% rule. And when we check the 5% rule, we're just making sure that we were allowed to toss out the quadratic equation. 0.0218776 set over that original value expressed as a percent. And we come out, oh, too large. So let's check that again. Remember, the original concentration was 0.01. This divided by 0.1 expressed as a percent, we get 21.87%. 21.87, it's too big, isn't it? We're not allowed to toss out x. I like to always assume we can, but we check it. In this particular equation, we're not allowed to toss out the x. We broke the 5% rule. That tells me, okay, nice try, but I got to back up. I have to use the quadratic equation. We have to account for x. That this ion, this molecule is dissociating to create more ions in solution. So back to work we go using quadratic equation. The Ka, 0.0047863, is equal to x squared. Now I have to go 0.1 minus x, solving for x. Here was the calculated value of x, tossing out the quadratic equation. Let's tackle it using the quadratic equation. 0.0047863 has to be distributed with 0.1 minus x, still equal to x squared. 0.0047863 times 0.1 is simply moving the decimal, so I'm just distributing that through, and we get, and let me just put it in scientific notation, 4.7863 times 10 to the negative fourth minus 4.7863 times 10 to the negative 3. And I'll bring x squared over, minus x squared, now equal to 0. You see what I did here? I moved the decimal 1, 2, 3 spots, and I just simply wrote that as 4 times 10 to the negative 3. Alrighty, so I just expressed both values. When we use our quadratic equation, a comes out to be negative 1. B is given as, whoops, I forgot my value of x right here. B is negative 4.7863 times 10 to the negative third, and the letter C has a value of positive 4.7863 times 10 to the negative fourth. Use your quadratic equation formula and see what we get for x. So programs, quad, the value of A, I type in negative 1. The value of B, negative 4.7863 0.863, E negative 3, and for the value of C, 4.7863, E negative 4. Notice that's positive on that value of C. The value for X I get, one is negative, we know to toss that out. 0.01961496, and again we can carry all those decimals. How much significantly different was that? Look at quite a bit. X, when we calculated using the quad formula 0196, and again, enough of a difference where we broke the 5% rule. So with the quadratic formula, we come up with a more accurate measurement of our pH. We let X represent the hydrogen ion. So to find pH, we have to negative log that value of X. Let me hit that on the calculator. Negative log 0.019, I'll carry these decimals, 6149. And last number 6. Do you find a value of 1.707? So carrying 2 decimal places, we get 1.71 as our pH units. 1.71. Now, with this problem, just to kind of reiterate, backing up this long journey, we broke the 5% rule. I like to try it first, make the calculations easier, taking 0.1 times the calculated Ka, square rooting to find the value of X. When we check the 5% rule, just remember what we're checking, percent ionization. What's the concentration of the hydrogen ion at equilibrium compared to the concentration of the molecular acid initial expressed as a percent? That's what I did here. Calculated value of X at equilibrium divided by the initial concentration of the acid. It was far too large to assume the 5% rule. So we had to back up and use the quadratic equation. pH of saccharin at those conditions, 1.71. We have one more to work. It's number 65, which I understand on our homework paper it said 55, but that was indeed number 65 would be the next odd number assigned. Calculate the percent ionization of hydrozoic acid, HN3, not to be confused with ammonia, NH3. Let me just write that randomly up here. This is a base, ammonia. I just did that backwards. NH3 is ammonia. Here is an acid. Here's its proton here, HN3, hydrozoic acid. In solutions with each of the following concentrations, Appendix D is required simply because we need to look up Ka value of hydrozoic acid. You've been given an Appendix D, hydrozoic acid, HN3. Skim through that with me and see what you find. It's approximately halfway down your Appendix D. See where it is? Right under formic acid. The Ka value I'm finding for HN3 is 1.9 times 10 to the negative 5th. We want to calculate the percent ionization in each of the following solutions. So what will happen is the initial value of the concentrations of the acid indeed change. Alrighty. So here we have our Ka constant. Let me just work the first one where you have 0.4. So I'm going to rewrite this equation just to show the conjugate pairing. I'll show that as an equilibrium where H positive and the conjugate base N3 negative. We'll set up an ice chart where the initial concentration of the acid for part A is given to us as 0.4. We know initially there would yet to be any ions forming, so those values are 0. We know that reactants get used and products get made, so we'll let the change row be represented by the values of X. X decreasing, so at equilibrium we have 0.4 minus X. Here we'd have a value of X, and here we have a value of X. Let's calculate the percent ionization. All that's asking us to do to find percent, we want to know the concentration of hydrogen at equilibrium, that's this box, isn't it, compared to the original concentration of the molecular form of our acid, initial. The X value over the original value. Alrighty. So, let me give myself some work room here, erasing the last problem. Thank you for your patience, making room here. Boy, that last problem took some space. Hope you're fast forwarding. Here we go. All right, so here we have the values we need in terms of the initial and the values of X. We found Ka to be a constant, 1.9 times 10 to the negative fifth. So 1.9 times 10 to the negative fifth is equal to X squared set over 0.4 minus X. Notice I'm not assuming the 5% rule. We're going to just put in 0.4. But again, if I did assume the 5% rule, let me just set that up over here. 1.9 times 10 to the negative fifth equal to X squared over just simply 0.4. Let's solve that first, and if it gets us too big, then we'll have to back up and solve for the quadratic equation. Always assume less than 5%. Be pleasantly surprised if it works, and if not, then back up and use the quad formula. So with this particular key sequence, to pull out X, we will hit 1.9 e negative 5 times 0.4, and we get a value of X squared, 7.6 times 10 to the negative 6. We square root that answer, and the value of X came out to be 0.0027568. Plenty of decimals. Now here we let X stand for that hydrogen ion at equilibrium. Let's see what we get for percent ionization. 0.0027568 molar units of hydrogen set over the initial value of that molecular form of the acid, 0.4 molar, and I think I'll just write HA for any generic acid, expressed as a percent. So divided by 0.4, expressed as a percent. This was valid math. Did you find for your percent ionization 0.689? So how about 0.69%, which is well below the 5% rule, which means we could indeed toss out the minus X here and do simple math. 5% or below, no need for the quadratic formula. Now, does that math continue? All right, so let's see this. If indeed we had 1.9 times 10 to the negative fifth was Ka, set equal to X squared, but now notice for part B, the concentration has changed. Part A we did 0.4 molar. Down here we have 0.1 molar, the original concentration. Let's find for X, once we know the percentage, we'll take a peek at 5% rule. So 1.9 e negative 5 times 0.1, square root that answer, and you're going to find X come out to be 0.0013784. There's your hydrogen ion at equilibrium. Let me hit my math again just to be sure I did it correctly. E negative 5 times 0.1, square root that answer. Hit it twice, I found the same answer, so I just like to know for sure. Now let's place that value of X over the original concentration of 0.1 molar and find the percent ionization. So my value of X divided by 0.1 times 100, and I'm at 1.37% ionization. I should probably round a little bit different. 1.38% ionization. Still, valid math, we're well below 5%. If the number comes out greater than 5, we back up and use the quadratic equation. Let's finish off the letter C and we'll have our homework completed. Letter C gives us the same Ka, 1.9 times 10 to the negative 5th. X squared, still representing the concentration of both ions, but now we have a much more dilute solution of acid, 0.04 molar of the HA. Cross multiply and square root to find the value of X. 1.9 e negative 5 times 0.04, square root that answer, and X comes out to be 8.717 times 10 to the negative 4th. That's representing the hydrogen ion at equilibrium. Back to that original ice chart. That's not yet changed. But now that original acid is 0.04 molar, I'll just write that generically as HA, expressed as a percent. So divide by 0.04 times 100, and we're at 2.17%. Again, the value well below 5, so we're able to toss out the quadratic equation. So this problem really allowed us to repeat, to just additionally practice. When I want to know percent ionization, we are comparing the hydrogen ion concentration at equilibrium to the original value of the acid initially, part over whole times 100 to express it as a percent. You've now completed lesson 6. I'd like you to turn that in. And from here, your assignment, again, if you're going back to your Moodle calendar, I want you to go back into your note packs and I want you to look at weak bases, the next lesson following your Moodle calendar.